I swear a lot, in fact. Now, was that funny? Notice I have not signed the video release. Now, to test this, right, you throw the old single quote in there, which is the age-old SQL injection test. It's just one of different ways. And you see we get a database error message back. The reason this occurs is because the web application takes that 2%, the two single quote, the code takes it, slaps it on the end of the query, and passes along to the database so that the query says select error message from error messages where error code equals 2 tick, right? And we get an ODBC error message back. Now the error message says unclosed quotation mark before character string tick, right? That's because a single quote or tick is a text delimiter in the SQL language. Therefore, it's expected in pairs. It's expected that error code equals single quote to single quote, right? User ID equals single quote, mat, single quote. When the SQL server gets an odd number of them, it throws up an error because it's unbalanced. Now, the error itself is a little bit pertinent. This is probably the most blatant error message when it comes to finding SQL injection. This is what people Google all the time. But the actual content of the error message doesn't matter as much as the fact that it comes from the ODBC layer. It comes from the database connectivity layer, not the web application layer. This is the database itself talking. So what this tells you is you put a completely invalid character into the web application. A single has absolutely no purpose in an integer field, right? The web application didn't sanitize it, filter it, validate it, whatever you want to call it. It took it, threw it against the database, then took the results from the database and printed the results back to the screen. Now in this case, the results were an error message, right? But that's irrelevant. This parameter in the query string, error code, now represents a two-way pipe to the back-end database. Whatever you put in there, within limits, the web application runs against the database and gives you results back. So what you have to do now is turn that from a broken query into a working query. The whole point of testing for SQL injection is to break the query, unless you're doing blind. It's a very different paradigm in blind. But when you're testing for verbose, which is the majority of SQL injection, you're literally just throwing junk in there to try and break the query. You can do that in a lot of different ways. You can do that with the classic single quote. You can do that with division errors, mathematical errors. You can do that by putting in a table name or a column name that doesn't make sense and look at the feedback you get. And again, this explains why the single quote is such an effective test. In reality, single quotes get filtered out quite a bit, but you can do other things. The same page, I throw in a blah after the two, and I get incorrect syntax near blah. It's an ODBC error message, which means that the word blah went to the database. I put in 2 and 1, and it says non-Boolean condition, right? I expect some sort of Boolean operator. Again, it's coming from the database. Script errors don't necessarily count. They might give you more clues to do stuff and try and get through to the database. But errors like this, typing errors especially, casting errors, come from the ASP environment or the web application, the PHP layer, not the database layer itself. So sometimes you'll go through like a single quote in something and you'll get a nice fat 500 back, you'll get the exception. But if it's not coming from the ODBC layer, it's not SQL injection. It might be, you just other tests. Once you find the ability to get unvalidated input into a database query, the goal then is to formulate something that makes sense to the database so it actually executes. Forming the useful query gets trickier. And let me caveat that all of these slides are pretty plain vanilla examples, right? SQL injection in reality gets very, very sophisticated very quickly. Especially when you start coming across random validators that mess up certain characters and not others. And it's one of those things that you have to kind of sit through and pull a lot of different SQL injection tools out of your box and play with to really get something through. But when it comes to vanilla, plain vanilla, straight up injections, there's plenty of them out there. A union operator works very easily, particularly against integers. And this is kind of the big argument against magic quotes. People believe that magic quotes actually breaks SQL injection. Does everyone know the full story behind magic quotes? Magic quotes was not built as a security function, right? I should have dug up the slides. 2 or 3 years ago at a law enforcement conference, I analyzed a worm. And the worm evaded magic quotes by doing a simple URL encoding. And I had slides of this interview with Rasmus Lerdoff where he explained where magic quotes came from. And it basically boiled down to I was going to emails a day from people saying my queries break, because people didn't realize that trying to insert a single quote into a database doesn't work. So magic quotes escapes them for you, and then you can use unescape functions. If you're injecting against an integer, you don't necessarily need to use single quotes for anything. In this particular example, I do, just to narrow the results of my query a little bit more, but I could have just as easily have left that off. When you go against an integer, in fact, when you go against any, when you suspect you're coming up against the tail end of the query, you can use the union operator. Union is a highly reserved SQL keyword, right, that should really never be accepted by any part of an application that uses a dynamic SQL query, particularly an integer field. The union keyword tells the database to expect two separate queries, right? It literally prepares the database to get two separate queries, in which case normally it would send two different record sets back, but it tells it to union the record sets, merge them back into one record set, and display all the results back in one record set. Now, the reason you use a union operator isn't so much to merge the record sets back, it's because it lets you send two different queries. The first part of the query is going to be the hard-coded one in the code, in the ASP or the PHP that you can do nothing about. The second part, of course, is your own query. And that's literally piggybacking on top of the programmers and executing your own queries. The queries you would typically execute first are going to be reconnaissance queries, right? Understand the schema, figure out where the interesting things are, and zoom in on that. Doing that on more enterprise databases is usually pretty easy. They have things like system tables that you can enumerate. Again, MS Access doesn't, so you literally have to brute force table names unless you can get some schema out of the error messages. It's kind of a pain. In the case of MS SQL Server, you can pull sys objects out of any database, and it will enumerate all the tables in that database. You can go up to master and pull sys objects from that. You can pull sys database from master. And look at all the databases on the server. Now, here's something interesting I discovered. On the job, after getting stumped a couple of times, I finally figured out why. Apparently, data reader and/or data writer can still enumerate master sys databases, so you can still see all the other databases on the server, but you can't traverse to them and use them unless that login also has permissions on those databases. But apparently, even if your login is mapped to one database with just read-write privileges and no DBO or admin privileges, you can still enumerate the rest of the databases on the server, which could be sensitive. When you find the tables you're interested in, sysobjects returns table names. You can then get column names from syscolumns. Syscolumns key is called ID, and it relates directly to the field called ID in sysobjects. So you can go to sysobjects, get the list of tables called bank logins. If you want to get the columns for bank logins, you have to have the ID field for the bank logins field. You can do that just in a select and say, error code equals 2, union select ID from sysobjects, where name equals, quote, bank logins, end quote. Or you can do this as a subquery and say select name from syscolumns where the ID equals, subquery, select ID from sysobjects where name equals bank cards. Either one will work. Once you have that, you have the table name, you have the name, and then you can go straight to row-level data. Yeah, it's credit cards. The neat thing about this is on a plain vanilla setup, a relatively easy setup, you can be inside row-level data in as little as 4 packets. It's plenty easy to find the injections themselves, especially if they're not stripping single quotes. And you can pull the table names out of sysobjects, pull the column names out of syscolumns, 3 packets, and then hit row-level data right in 4 packets. If it's SSL, it might not even be monitored. Now, again, SQL injection gets tricky. There honestly is a lot of plain vanilla SQL injection out there still, but SQL injection does get tricky, so there's lots of different techniques you have to be aware of, and you're going to have to use them and mix and match them on the fly. Nothing's guaranteed to work. I don't want to say it's a complex exploit. It's certainly nothing like overflows, but certainly nothing as easy as like reading backup. In the example I used, the ASP code iterated through the entire record set. So all the results that came back from the database got printed to the screen. That doesn't always happen, and frankly, that was bad code for that example, because that example page only used one return. It used one error message, so it really shouldn't have looped through. If you change that code to just write one record, right, then you have a problem, because you go to sysobjects and your table names, and you're only going to get one at a time, right? You can't get them all at once. Now, you can fix that by incrementing your queries. You can use Boolean operators against strings in SQL. MS SQL Server calls them varchars and nvarchars, not strings, but it's the same thing. So what you can do is restrict your first record to one result. And you want to make sure you get the top of the table. So you throw in a where clause, where 1 equals 1. And that's just, it's an old clause. It pulls back the first record, right? Then you get your first card number, social security number, login, whatever. You repeat the exact same query, but this time you throw in another where clause. You qualify a little bit further and say, this time I want you to pull back the next social card number that's greater than the one you just gave me. Greater than the one you just gave me. And sure enough, it brings back the next one on the table. And you just keep incrementing up that way. It can take a little bit of time. It certainly can be automated. One of the tools in our stuff automates the process. There are OS tools that do it, and certainly once you understand the methodology to SQL injection, it's easy enough to automate with Perl and wget. I want to make a quick note. This where 1 equals 1, if you have an IDS or an IPS, and they say they detect /block /eradicate SQL injection, take a look at the signatures. There's a lot of signatures out there where 1 equals 1. During pen tests, we don't do a lot of pen tests because we're a product company, not services, but during pen tests, we've come across devices and filters that were blocking things like where 1 equals 1. The evasion was really simple, where 2 equals 2. The magic is not the words where 1 equals 1. The magic is a true condition. It could be where z is greater than a, where 55 is less than 1,000. So your rule set, because there's actually a pretty decent chance that you have rules looking for literal expressions. Strings. There's no getting away from strings. You're going to have to deal with them at some point. And the way you deal with strings is by escaping out, right? Just like you do with script injection. In script injection, you have to escape out of tags. You have to escape out of other script blocks, or not. It's the same thing in SQL injection. In the first example, we were passing an integer back. So we could do a straight union. We didn't have to use any strings if we didn't want to. If we change this code to start passing a string, things get funky. Now, the way you pass a string is, first of all, the database has to be typed as a string. That column in the database has to be typed as an nvarchar. Otherwise, there'll be some explicit conversions going on. We'll talk about that later. Then your code has to do special things, right? Because if you stick the word mat into a database, it has to be wrapped in the single quotes. So now you start hard coding single quotes into your code. The original hard coding in the first example was select message from error messages where code equals. Then we just appended the request variable on there. Now we're going to be where code equals and a single quote. Now here it's 3 quotes in a row, but it's single quote and then end our ASP text line. And then the request object, and then we're going to start another ASP text line and throw quote in there. There should actually be a 4th in there. So now everything that comes from the request is going to be stuck between single quotes. That causes a bit of a problem because now if we throw in like a union clause, that in our whole second query gets stuck in between the quotes and sent to the database as a string. So the database will look for an error message called union select name from sysobjects. You get away from that by escaping your injection with single quotes.